Welcome, class. So in our previous sessions, we've really been laying down a strong foundation in mathematical theory. Today, though, we're going to bridge that theory with some very real-world application. We're moving from the abstract world of equations to the concrete challenges of business strategy. We're going to explore a concept that probably seems familiar from your algebra days, the quadratic function. But I want you to kind of set aside what you think you know. We are not just solving for x today. Instead, we're going to dissect this incredibly powerful tool and understand how it becomes a cornerstone of strategic decision-making for any manager. By the end of our time together, you won't just understand the how, but more importantly, you'll get the why. Why this elegant mathematical curve is so fundamental to answering questions about pricing, about production levels, and of course, the ultimate goal for so many firms, maximizing revenue.
Now, I want you to really think about this question. It's a tension that exists in every single boardroom, every marketing meeting, every business plan. On one hand, you've got the impulse to set a high price. I mean, a high price per unit, it just feels good, right? It suggests a high margin. But what's the inevitable consequence of that? Well, you limit your market. Fewer customers are willing or even able to pay that premium. So on the other hand, you could slash your price, and you'd probably see a huge surge in sales volume. But at what cost? You might be selling a massive number of units and still be struggling to turn a real profit. You see, this is not a problem that can be solved by intuition or some kind of gut feeling alone. This is where business administration really becomes a science. The mathematical models we're going to build today, all rooted in the quadratic function, give us a rigorous, data-driven way to navigate this exact dilemma and to pinpoint that optimal balance, that sweet spot where revenue hits its absolute peak.
To make sure we cover this with the depth and clarity it deserves, I've structured our lecture into 5 distinct parts. First, we'll establish the theoretical foundation, really getting a handle on the concept of the revenue parabola. Second, we'll move from theory to practice by actually building a revenue function from a demand equation. Third, once we have our function, we'll use its properties, specifically the vertex, to identify that point of maximum revenue. Fourth, and this is absolutely crucial, we'll translate our math into actionable business strategy. And finally, we'll wrap up by looking at some common pitfalls I see students make, just to make sure you can apply these models accurately and avoid some costly errors in a real business setting. All right, let's peek.
Okay, let's dive into our first section, the revenue parabola. The core idea here is to challenge a very common and frankly overly simplistic assumption about business, the idea that more sales always equals more revenue. We're going to see how a simple shape from geometry, the parabola, gives us a much more sophisticated and accurate model for understanding the complex dynamics of a marketplace. This is really our first big step in moving from simple, linear thinking to strategic, non-linear analysis.
I want you to really visualize this with me. Let's call it our revenue mountain. At the very beginning, if a company sells 0 units, its revenue is, well, it's 0, of course. Now, as they start to sell their first few units at a certain price, revenue begins to climb. This is the initial upward slope of our revenue mountain. But now, think about the law of demand. To get more and more people to buy your product, what do you usually have to do? You have to lower the price. So there comes a critical tipping point, the peak of our mountain, where the extra money you get from selling one more unit is completely canceled out by the money you lose from having to sell all the other units at that new, lower price. If you keep lowering the price past this peak, your total revenue actually starts to fall, even though you're selling more stuff. This is the downslope of our mountain. The key takeaway here, and it's fundamental to everything else we'll do today, is that there is a point of diminishing returns. Selling more is not always better for your total revenue.
Okay, let's formalize this idea with the equation you see here. This formula, r of x equals p of x times x, is the mathematical engine that's going to drive our entire analysis. Let's break it down carefully. R of x is our total revenue. And notice the notation, it's not just r, it's r of x, which tells us that revenue is a function of x, where x is the number of units you sell. That part's pretty straightforward. But the really crucial and often misunderstood part is p of x. Notice that price is also written as a function of x. That is not an accident. It represents a fundamental economic principle. The price you can charge isn't some constant number. It actually depends on the quantity you're trying to sell. To sell more units, to increase x, you typically have to lower the price. It's this interplay, this multiplication of a decreasing price function, p of x, and an increasing quantity, x, that gives birth to that parabolic shape of the revenue curve. It's what creates the mountain we need to climb.
All right, that brings us to our second section. Now that we've established the theory behind the revenue parabola, we're going to roll up our sleeves and actually build our mathematical model. And the starting point for any model like this is the most foundational piece of market intelligence a business can have, the demand function. It's what mathematically describes the relationship between the price of a product and the quantity that consumers are willing to buy.
So, the process for deriving the revenue function has 4 very logical steps. Let's walk through them. Step 1. We always begin with the demand function, which usually comes from market research. In its standard form, it expresses quantity demanded, X, as a function of price, P. Step 2. For our revenue model, we need to flip this relationship. We do a little bit of algebra to isolate the price variable P. This basically reframes the question from how many will we sell at this price to what price do we need to set to sell this many. Step 3. This is the critical substitution. We take that new expression for price we just found and we plug it into our fundamental revenue formula, R of X equals P of X times X. And finally, step 4. We simplify the whole thing. We expand it out, combine terms, and this last step is what will reveal that quadratic nature of the function and put it into a form we can actually analyze.
Let's apply those steps to a real example. As you can see in the table, our starting demand function in step 1 is x is equal to 1500 minus 50p, a simple linear function. Now in step 2, we solve for p, so we can add 50p to both sides and subtract x from both sides. That gives us 50p equals 1500 minus x. Then we just divide everything by 50, which gives us p equals 1500 minus x divided by 50. Now, pay close attention to step 3. We substitute this entire expression for p right into our revenue formula. So that gives us Rx equals 1500 minus x divided by 50, all of that multiplied by x. In step 4, we just cleaned it up. We distribute the x into the numerator, which gives us Rx equals 1500x minus x squared divided by 50. I want you to just pause for a second and appreciate what just happened. We started with a simple linear relationship, but by multiplying price by quantity, we've introduced an x squared term. This is the mathematical birth of the parabola. We've successfully translated a market condition into a powerful quadratic function that models our total revenue.
Okay, this brings us to the analytical heart of today's lecture. We've successfully modeled our revenue with a quadratic function. We know, conceptually, that this function represents a parabola that opens downwards, which means it has a maximum point. The question now is, how do we find the exact coordinates of that peak? We're not interested in guessing here. Business strategy needs precision. And thankfully, mathematics provides us with a direct and, frankly, elegant tool for exactly this purpose, the formula for the vertex of a parabola.
Now, before we can even think about using the vertex formula, it is absolutely imperative that we first put our revenue function into standard quadratic form, which, as you'll recall, is ax squared plus bx plus c. Our current function is r of x equals 1500x minus x squared divided by 50. To convert this, we just divide each term in the numerator by the denominator, 50. So negative x squared divided by 50 gives us our a term, negative 1/50th x squared. And 1500x divided by 50 gives us our b term, plus 30x. So our function in standard form is r of x equals negative 1/50th x squared plus 30x. Now we can clearly identify our coefficients. A is negative 1/50th and b is 30. You might notice the c term is 0. And that should make perfect sense from a business standpoint, right? If you sell 0 units, if x equals 0, your total revenue should be 0. This little bit of algebraic housekeeping isn't just a trivial step. A mistake in identifying A or B here will make every calculation that follows completely wrong.
And this formula right here, x equals negative b over 2a, is the key to our entire problem. First, let's just confirm it's the right tool. The sign of our a coefficient was negative 1/50th. It's negative. That confirms that our parabola opens downwards, which fits perfectly with our economic model of a revenue curve that has a single peak. So this formula is going to give us the x-coordinate of that peak, the vertex. And in the context of our business problem, what does that x-coordinate represent? It represents the exact quantity of units that the company must produce and sell to achieve its absolute maximum possible revenue. It is the answer to the how many question.
All right, let's actually do the calculation. We're going to substitute our coefficients right into the formula. So the formula is x equals negative b divided by 2a. Our b value is 30, so negative b is negative 30. Our a value is negative 1/50th, so 2 times a is negative 2/50th, which simplifies down to negative 1/25th. So our expression becomes x equals negative 30 divided by negative 1/25th. Now you have to remember your rules of algebra. Dividing by a fraction is the same as multiplying by its reciprocal, so this is the same as negative 30 multiplied by negative 25. A negative times a negative gives us a positive, and 30 times 25 is 750. So we've arrived at our solution, x equals 750.
Let's just pause on this number for a moment. 750 is not just the solution to a math problem. For a business manager, this number is a critical piece of strategic intelligence.
This is the production target you send to the operations manager. This is the sales goal you give to the marketing and sales teams. Based on our model of market demand, producing and selling precisely 750 units will result in the maximum possible revenue for the company. Any more or any less, and that total revenue will start to go down.
So we've answered the question of how many. We know the optimal quantity is 750 units. But that's only one piece of the puzzle. A sales team can't really act on that information alone. We have to answer the second critical question: at what price? We have to figure out the specific price point that, according to our demand model, will cause consumers to buy exactly 750 units.
To find that optimal price, we have to go back to the price function we derived way back in step 2. Remember that one? It was P equals 1500 minus X divided by 50. Now we just take our optimal quantity, X equals 750, and we plug it right into this equation. That gives us P equals 1500 minus 750 divided by 50. The numerator becomes 750. So we have 750 divided by 50, and that calculation gives us a result of 15. So the optimal price to charge for our product is $15.
Okay, so now we have our two key strategic outputs, an optimal quantity of 750 units and an optimal price of $15. This brings us to the final and maybe the most important part of our analysis. How do you translate these numbers into an actual business strategy? How does a manager in the real world use this information to guide their company? This is the bridge between the quantitative analysis and real managerial decision-making.
I want you to imagine you're in a strategy meeting. The head of marketing says, "Hey, our brand is premium. I think we can get $16 for this product." A manager who's done this analysis can confidently say, "I understand wanting to increase the price, but our model shows that at $16, we'd only sell 700 units. That's a total revenue of $11,200. It's actually less than we could be making." Then maybe the head of sales chimes in. "We need to move inventory. Let's do a big sale at $14. The manager can then reply, "At $14, we would sell 800 units, but our total revenue would also be $11,200. Our analysis has proven that the revenue maximizing point is precisely $15, which lets us sell 750 units and brings in a maximum revenue of $11,250. Do you see the power in that? It's not about opinions anymore. It's about using a quantitative model to defend a strategic position and make data-driven decisions with confidence.
We'll now move on to our final section, and it's a very practical one. In all my years of teaching this material, I have seen several common areas where students can make small but very critical errors. These aren't necessarily difficult concepts, but they do require some careful attention to detail. So our goal here is to identify these potential traps so that you can consciously avoid them in your own work, both in this class and in your future careers.
Please pay very close attention to this one. The single most frequent error I see is a misinterpretation of what the vertex formula actually tells you. A student will correctly derive the function, correctly apply the vertex formula, and get the right answer, x equals 750. Then, on the final exam, they will write, "The optimal price is $750. This is a catastrophic error. It comes from forgetting what your variables represent. The vertex formula, x equals negative b over 2a, solves for the x-coordinate of the vertex. In our model, we explicitly defined x as the quantity of units sold. The formula tells you how many to sell, not the price. To find the price, you must always perform that final crucial step. Substitute your optimal x value back into the price function. I cannot stress this enough. Always be mindful of what your variables mean."
And let's discuss 3 other points of caution. First, just good algebraic discipline. Always convert your function to the standard ax squared plus bx plus c form before you do anything else. It is the only reliable way to identify a and b. Second, be meticulous with your signs. The vertex formula has a negative in it. A simple calculation error, forgetting a negative sign on a or b, will completely throw off your result. Double-check your arithmetic. And finally, this is a huge conceptual point. Never, ever confuse revenue with profit. What we've done today is find the price and quantity to maximize a company's total income. That is not the same thing as maximizing its profit. Remember, profit is revenue minus costs. It is entirely possible that the revenue maximizing price is not the profit maximizing price, especially if costs change as you produce more. Understanding this distinction is vital, and it's actually the topic we'll be turning to in our very next lecture.
And so we'll conclude with this forward-looking question. We have absolutely mastered the art of maximizing revenue. But what happens when we introduce the reality of costs? What if you have fixed costs for a factory and variable costs for every single unit you produce? How does that change our model? How does it shift our optimal price and quantity? The analysis we did today is the essential first half of a complete profit maximization model. The skills you practice, deriving a function from a business condition and then finding its maximum value, are the foundational tools you will need as we move into the even more complex and realistic world of profit optimization. I encourage you to think about how you might start to incorporate costs into this model before our next session. Class dismissed.